Okay, good afternoon. So today we'll continue talking about demand paging. Hopefully there's not much left, so we get to start talking about I/O. Okay, so just a reminder, last time we talked about LRU. We said that implementing LRU is too expensive, so we need to approximate that. And the way we approximated it was through clock algorithm. Then we said that clock algorithm is basically too coarse grained. So our the way we talked about implementation of clock algorithm was that at every page fault, we categorize pages into those with valid bit equals 0 and those with valid bit equals to 1. So pages here are safe, so we're not going to evict them. Pages with valid bit here are potential victims. Now, which one do we choose? The one that the head is looking for or pointing to. So this is how we were doing it with clock algorithm. Now, this basically doesn't give us any good information about, from these pages in that have valid bit 0, which one is the one that was addressed or accessed the least. We don't know. So all of them are the same for us, right? And we're just going to look at the one that has the head is looking at. Now, with nth chance algorithm, we're going to divide pages into more groups. So we're going to divide the one from n-1, n-2, and then all the way to 0, right? So, and then we're going to pick our victim here. Now, this is much better because we know that pages that are here, we haven't been accessing them for n different iterations. Whereas someone that is here, we haven't only been not accessing this for 2 iterations, right? So we kind of know that the pages that are a particular page here compared to a particular page here, the page with that is categorized here hasn't been accessed for a longer period of time compared to a page here. So this having more fine grain classification provides better approximation of LRU, right? With LRU, really we have this n is infinite, right? So we have this accurate list of all the accesses that we have accessed. So we always pick the one that is the bottom of the list, not necessarily 0, but the one that has been accessed the least, right? So with nth chance algorithm, by making more classes, we kind of distinguish between the ones that have valid bit 0. We know some of them haven't been accessed for a longer period of time than others. Whereas with the original clock algorithm, everybody with valid bit 0, we will treat them all the same. We didn't have any more information on which one of them was the one that was accessed the least. So that was the idea behind nth chance algorithm, and that's why it's better. We also talked about excuse me. We also talked about how frequently we should run the clock algorithm. The original option was to just run it every time you get a page fault. An alternative is to just periodically run it in the background and always have a list of candidates to be to be evicted. Okay, now I want to, so the last topic that we're going to talk about is a topic that we kind of mentioned when we started talking about memory management. So I just, as a reminder, when I started talking about memory management, I said that we have two main tasks with memory management. The first task is to do memory protection and isolation. So the main goal, that the main topic of our class for the past few weeks has been talking about address translation as a mean to achieve memory protection. The second task was allocation. So here it comes. I'm not going to spend that much time on allocation, but it's part of memory management. So how much physical memory do we allocate to each process? That's the topic we're going to discuss. How do we decide how much physical memory do we give each process? That's the problem that is going to be discussed. Well, each process needs a minimum amount of memory to operate, right? If you do not bring the code or the executable image of a process, it can't execute possibly, right? So there is a minimum amount of memory that you need to at least start executing your code. Now, let's say that you allocate memory initially to your processes. Let's assume that you give one process 1 GB and another process 5 GB, sorry, 50 megabyte, and another process 500 megabytes, and another process 2 GB. So let's say we start with an allocation. Is that enough? So if we start with an allocation, does that mean that we're good and this allocation remains the same? The answer is not really. It depends on the replacement policy. Now, let's say let's say process 1 got I don't know, 50 megabyte and it needs more. So what's going to happen is it's going to ask for more. Now, if you have memory available, you're going to give it to him, to this process. If you don't have, then you want to do demand paging. You're going to pick a victim and bring the page that process 1 wants. Now, if the victim is a page for process 2, what this means is you're going to get away the allocation you gave process 2 and give it to process 1. So this is basically global replacement. So if you allow your victims to be from any process, then there is a chance that you're going to change your initial allocation. So whatever allocation you started with will change as time passes by, because you're going to take away pages from one process and give it to another one. Now, an alternative to this is to do local replacement. Now, if process 1 wants to bring a new page to memory, the victim has to be one of its old pages. So this way, we are not going to take away any physical page from another process. So if you really want to enforce allocation, you also have to enforce allocation in your replacement policy. Now, one way of allocating is through fixed priority. Now, we're going to assign priority to our tasks, to our processes, and then allocate memory based on their processes, their priorities. Now, the first option is to give everybody the same priority. So everybody is the same. This leads to equal allocation, obviously, right? So if everybody is the same, then everybody gets the same amount of memory. This is obviously a bad allocation because not everybody needs the same amount of memory. And if you give everybody the same amount of memory, the one that needs more is going to be experiencing a slowdown, and the one that doesn't need what you have given them, they're going to waste your resources. The second option is to do a proportional allocation based on the size of each process. So you could potentially look at the number of virtual pages, the size of each process, basically how many pages they use, and then allocate your memory based on that that metric. So let's say that let's say SI is the size of process I, meaning that how much memory that this process needs. And let's define capital S to be the summation of all these sizes. Then proportional allocation means that each process, let's assume that there are only M pages available. So the share of each process becomes SI times M divided by capital S. And you can see that the sum of PI is basically M. So we're going to allocate the entire space, and we're going to give everybody an allocation that is proportional to their size. Now, this is really good for performance, right? Because you're going to give more to the one that needs it more, and it's going to be good for performance, but not necessarily good for fairness, because what if one process, is asking and demanding for more than its fair share. Another possibility is to design a priority interface and ask your users to tell you what the priority of each task is, very similar to our system in your labs. We can set priorities, and then we can assign allocation. We can allocate memory based on the user-defined weights. So if one process has twice as much weight as another process, then we make sure that its allocation is twice as much as the other one. So basically, everybody gets a weight, WI, let's assume, and then we do the same thing that we did with S, but this WI is basically user defined. The user tells us what the allocation is. And this is very typical in cloud computing and in data center environments where you have different VMs from different users, and then depending on how much money they have paid, you can set their importance, their priority, their weight, and then reinforce that. Now, how can you use this fixed priority allocations? You can do it statically, so static allocations, meaning that you allocate memory and you don't change it. So as long as your application has it, is running, has the same amount of memory all the time. So this is one option, obviously not attractive because our processes go through phases. In one phase, your application might need more memory. In another phase, it might not need that much memory. So if you fix the memory allocation, you're wasting resources. So an alternative to this is dynamic. Is dynamic allocation. So you could adaptively, for example, change the priorities. You can adaptively, for example, look at how much memory each one of them wants and then allocate based on that. So we're going to talk a little bit about this dynamic allocation in a few slides. But the simplest way is to just do it statically. Okay, now let's look at one of the signals that we can get when we want to allocate memory. So if you remember from previous lecture, I showed you when I was talking about the anomaly in replacement policies, I showed you a graph like this, where on the x-axis you have the number of pages that you're allocating to a process, and on the y-axis you have then the page fault rate, how often this process gets a page fault. Now, the more you allocate to a process, the less page faults the process is going to see. And that was something that we expected. Now, when you're dealing with, when you're thinking about memory allocation, you might actually have an upper bound and a lower bound on the acceptable or desirable page fault rate. Now, what you could do is, so if you actually have this curve, let's say for process 1, this is the curve. For another process, maybe the curve is like this. So this is for process 2. And then maybe for process 3, the curve is like this. So if you have this curve, well, you can easily look at these two to identify the minimum allocation for P1 and the maximum allocation for P1, right? Because as long as you allocate anything in here, your page fault rate is within the range and you're safe. So the maximum you need to give it is this P1 max, and the minimum is P1 min, for example. So these are how much memory you have to give your application to make sure that your application's page fault rate is within the desirable range. And this could be different for different processes, depending on their characteristics. You know, how much memory they need could be different. Now, in reality, you usually don't have these curves, right? You don't when you start the operating system, when it starts executing a program, we don't know what this curve, how this curve look like. Now, an alternative to this is to just try and error, right? How so? Like, what you could do is, let's say you don't exactly know this curve, so you start with some allocation. So you give your process some number of pages, and then you measure the page fault rate. Sorry for this. So you measure the page fault rate, and you realize that this is not good. It's more than what is desirable. So what you do, you increase the allocation. So you give the process some more, and then you measure again. And hopefully you bring it down to your desirable range. So when you come to the desirable region, you're good, right? Another scenario that could happen is you might give your application too much. So you could start here and you measure your rate and you see that the rate is really low. This means that you have given your application too much. So then you might want to decrease your allocation to see if you can get this rate within the range that that is desirable. So basically, if the rate is too high, it means that you have given it too little, so you have to give it more. If the rate is too low, then it means that you have given it too much pages. So you can take back some of those pages. Now, on a related note, I don't exactly know if you guys have experienced such a scenario, but in olden days, when computers were not as powerful as this, as today's computers, we would start like running some programs. For example, you would open your web browser, and then you would open your Microsoft Word, and then if you had opened your your Photoshop or some video editing program, all of a sudden your computer would crash. So it would get so slow and nothing would get done. And then you have to go back and close those processes that you opened before. What was happening is explainable by page faults, and it's called thrashing. And you probably have heard of it in ECE 252 when you talked about swapping. So it's probably just a reminder for you. But what is happening is, as you increase the number of processes in your system, especially in a multiprocessor system, you start improving your CPU utilization. So in the graph that you're seeing on the x-axis, I have the number of processes that are open, and on my y-axis, I have the CPU utilization. So the more applications I'm running, the busier my CPUs become, right? My CPUs become busy. They're doing a lot of work, so everything is fine. Until at some point, the system crashes. So the CPU is no longer doing anything. But the system is not working at all. So what is happening at this point is that your processes start kicking each other's pages out from memory, or for that matter, their own pages, because we don't have enough memory. So you start wasting CPU cycles to run demand paging and page fault handler. So the rate of page faults goes up because there is not much physical memory left. The demand for physical memory is more than what we have. So we start getting page faults a lot. And each page fault basically uses CPU. So the CPU, instead of going to do actual work to do the applications that we're interested, the CPU cycles go to run page fault handler. So I guess you guys have seen the solution. When this happens, obviously you will notice the system starts, the performance of the system starts degrading, and the rate of page faults goes up. One of the solutions is to kill the process, that one or two processes, you can kill them. And that's very harsh, but possible, to then make a space for the rest of them. An alternative is to just swap processes to disk, as you kind of saw in ECE 252. Okay. Now, here is the slide I'm going to talk about dynamic memory allocation, and also we'll talk about a notion of or a mechanism to detect thrashing. So we're going to kind of connect the two topics that we talked. One was dynamic allocation, one being thrashing. So we're going to, I'm going to introduce something, and then we'll talk about a mechanism that can work for both of them. Okay, so what are we looking at in this slide? Excuse me. So in this graph, on the x-axis, I have time. I have execution time of my process. On the y-axis, I have memory addresses. Now, let's say my application accesses a certain memory. So each point here, any point in this graph, indicates that my application accessed this particular memory, this A1 memory address, at this particular time. So at T1 or T whatever, my application accessed this address A1. Now, so that's the meaning of each point here. So for every access, I tag it with the time that access happened, and then I plot the scatter file for this, scatter plot, to see which addresses have been accessed at which times. Now, what I can do with this is to then draw these rectangles around these black regions, which have a lot of points. And then let's see what we can understand from them. So this basically means that in this delta t, so in this period of time, from this time to this time, I have been using this delta A. So there is a range of addresses that I have been accessing for a period of time. What does it really tell you? This is kind of like both temporal locality and a spatial locality, right? So this basically says that these addresses, the same address, is being used again and again and again in this time period. It also says that within the same time period, these addresses that are close to each other have been accessed. Now, we call this a working set. So what is a working set? A working set is a set of pages. So basically this guy, delta A, the set of addresses, the set of pages that we have referenced in a sampling window. So this is our sampling window, this delta T. So this basically defines a working set. Now, if I look at my application at any given time. So let's pick this time here, and I look at, this is a window of time, and I'm going to look at the working sets that my application is accessing. So there is one here, there is one here working set, there's one here. There are more, right? So that you might actually consider this, there's this one here. So these are the different working, I haven't shown you all the working sets in this figure, but you get the idea, right? Now, what can I do with this? If I look at a graph that shows me hit rate on y-axis, the number of, the rate at which I hit in memory. So I'm looking for a certain page and I find that page in memory. And then on the x-axis, I have the memory allocation. Now, what is happening is, initially, if you don't give me any memory, I'm going to just keep missing in memory because none of my pages are there. You start giving me more and more and more and more memory, so I can start bringing in my first working set. Let's say I bring this working set here, working set number 1, I bring it. Now, once this is in memory, all of a sudden I get a boost in my performance. Because now this working set is in memory, so all my accesses to this working set will hit in memory, and my performance is boosted. The number of page faults that I'm going to see goes down. Then you start giving me more, and more memory, so I can fit my second working set. Now again, I get a boost here. Now, for the third one, you start giving me more and more memory. At some point, I can fit this new working set. And again, I get a really good boost in my performance because now I have 3 of my working sets present in memory, which means that any address, any access to these pages are going to hit in memory and not create a page fault. And so on and so forth, right? So this is the explanation of these jumps in the hit rate. This means that I have enough memory to bring in a complete working set. Now, here comes an algorithm that we can use for both allocation and for thrashing. So basically, we don't have this plot at the beginning when we start, running an application. We don't exactly know what pages this application is going to need at any given time, right? You can get this after you finish your application, your process, but when you start your process, you don't have this. So how can you construct such a thing? What you could do is at any given time, so let's say T1, you can look back for a period of time. This is your sampling period. You can look back at certain number of instructions or certain amount of time, and then look at all the pages that you have accessed in this window. And then you can construct this set of unique addresses, unique pages that you have accessed. And this becomes your working set. So this is a set of pages that you have accessed in the previous time window. Now, at some other time, let's say T2, if I look back at the same window of time, I might get a different working set. So at this time, if I look, I'm using page 4, I'm using page 3, page 4, page 3, page 4, page 3. So I'm only using page 3 and page 4. So my working set has shrinked to 2 pages. And those 2 pages are actually different from what it was at time T1. Now, how could this come handy? Well, the first thing, before actually talking about the use case for this, let's talk about this time window, this sampling period. How large should this sampling period be? Well, if it is too small, if it is too short, then I'm not going to get enough information about the pages that I need because it's so short term. If it is too long, then I might get too much information that I don't need. For example, if I look at a long delta here, then I might say, oh, I need 3, 4, 1, 2, I don't know, 5, 6, and 7. And in reality, I'm no longer using these guys, but it would come in my working set, and basically my working set estimation would be off. So picking this window size to be a right size is important, and it would really depend on applications, the applications that you're running. Now, we all know that if you set this window time to infinity, this basically means that you're going to look at all the pages that you have used from the beginning of your program until now. So it's very inaccurate. You're basically looking at all the virtual pages that your program has used. And it's useless, right? It's kind of like, it becomes like the size of your process, all the virtual pages that your process needs. Now, one thing you can do with this algorithm, with this estimation of working size set, is to detect if you have thrashing, because the sum of the size of these sets. So at this point, maybe the size for process 1 is 2. The size of this set for process 2 is, let's say, 10. And so on and so forth. Then you can do a summation, and this tells you what is your demand, how many pages are your applications and processes asking for, and then you can test this D. You can check it with how much memory you have. If D is less than M available memory, then you're safe. So you have enough pages for everyone. If, however, D is more than M, this could mean that you're starting to thrash the memory, because then demand is more than the available memory, the available number of pages. The other thing that you can do with this is, if you remember, I talked about size of process. So I said you can allocation of agent I could be SI times M divided by capital S. Now, in that slide, I said S could be just the size of the process, but instead we can just use the WS. So working set, the size of this times M divided by the demand, which is the sum of all working sets. So this gives us dynamic allocation, because this working set size is changing over time, and then we can just change the allocations as we proceed. Okay. Okay. So this slide is basically talking about prefetching. So it's so basically the idea is that you could prefetch pages, and the way you could do it is that if you get a page fault for a page, you could assume that probably the application is going to ask for pages that are close by. Of course, this should be in virtual address space. So if you get a page fault for virtual page 10, you might want to assume that probably you're going to get a page fault for page 11 and page 12 maybe. So you could potentially prefetch those pages as well. But then we also talked about, you have to be careful when you're doing prefetching, because you could allocate too much memory to pages that you're actually not going to end up using, right? So when you're doing prefetching, you have to be careful in bringing pages to memory. Okay. The last topic I'm going to talk about to finish up our discussions on memory management is about reverse page mapping. Now, the idea is, so far we have been talking about virtual page to physical page translation, and that was necessary for every access to memory. But do we also need to know physical page to virtual page mapping? Why is that even important? So let's say you want to evict a page. So what are you going to do? So if you evict a page, you have to go and invalidate its virtual page. Its translation in page table entry. Now, you remember that different processes could share memory. So a single page could be assigned to multiple processes, not just one, but multiple. Now, if you don't have the mapping from physical to virtual, every time you evict a page, you have to search all the page tables to see who was using this physical page so that you can invalidate those entries. And this is too expensive. This motivates the fact that we actually need both ways. We need to know which virtual pages are mapped to which physical pages, and we also need to know which physical pages are mapped to virtual pages. So yeah, so again, we talked about sharing. We talked about, you have to go and invalidate. So you could, there are different ways to implement this. You kind of want to have it both ways. Have a mapping from virtual page to physical page, and also have mapping from physical page to virtual page. Okay, so that's that. So we're done with memory management. so let's move on to the next topic, which is I/O. So I'm probably not going to be able to cover everything in my slides, because otherwise we won't be able to talk about file systems. So I'm probably going to forego this one. I'm with high probability not going to talk about I/O performance. So we just talk about I/O subsystem, and then we move on to storage devices. Okay. So far we have been talking about CPU, we have talked about memory, but then as a computer system with just CPU and memory is very boring. It doesn't have use for us. So a computer becomes interesting when it starts getting, accepting input and providing output, when it starts communicating with the users. Now, there are a range of different devices for communication. So, for example, for input, you have your microphone, for example, your camera, your keyboard, your mouse, you name it, your different types of USB devices. These are input devices that you provide input to your system. And then there is a range of output devices, like, for example, I don't know, your printer, your display, your sounding system, to some extent your SSD, for example. Now, these different devices have different characteristics. And in this slide, I'm just looking at one particular characteristic, and that's basically the I/O transfer rate. How fast can CPU send data to a device? And as you can see, there are devices in this figure down here, down the spectrum, like your keyboard, your USB, your Bluetooth. These are really slow. So the number of bytes that you can transfer to these devices is very little. And then there are these other kinds of I/O devices at the high end of this spectrum, where, for example, you have PCIe Express devices. These actually can accept gigabytes of data per second being transferred. For example, your GPU or your SSD or your fancy network card could accept gigabytes or megabytes of data per second. Now, this is just one aspect. If you look at the higher end and the lower end of this spectrum, there are, like, I think at some point I did the calculation, 7 order of magnitude difference. It's not 7x, it's 7 orders of magnitude difference between the transfer rate of these two ends of the spectrum. And again, this is just one aspect. You could potentially look at other aspects of devices, like the range of different protocols that they support, for example. And this is another reminder to all of us that as an operating system, our job is to hide all of this from the end users. This allows hardware device providers, device producers to expand this range, to come up with newer designs, to make this a lot faster, to have something here in between. So they can do whatever they want, and then the software developers don't need to worry about all these different ranges of data transfer or all these different ranges of protocols, for example. So we're going to be there hiding all the characteristics and the differences between our different devices. That's our job as the operating system, to basically hide this. But then this is a reminder that, well, this could potentially make our job really hard, because we have to come up with mechanisms and interfaces that work well with these devices. It also work well with these devices. So this is the part that makes our life hard, because, you know, we have to kind of deal with all sorts of devices, and whatever interface we're designing has to be able to, you know, address the difficulties and the challenges of each one of these different devices. Now, the goal of the I/O subsystem in the operating system has to be providing this uniform interface, right, as we discussed, for all different types of devices. Now, in Linux kind of systems, one example that you see, and you have probably seen this in ECE 252, is that, you know, one of the interfaces, one of the unifying interfaces that we use is to treat devices as files. So you give each, you mount each one of your devices to some file address, and you start communicating with your devices through read and write to that device. You read, you write to that file from that file, and this way you're communicating with your device. So this is one example for what we mean by unifying the framework. Now, let's look at different kind of interfaces, different requirements for different devices that we have to be aware of. And this is, again, just scratching the surface. So one aspect that we have to consider is data granularity. What is the unit of data that I can send or receive to and from my device? And this is different. So some devices, like your keyboard, for example, the unit is just a byte. So if you want to communicate with the device, you're communicating on granularity of bytes. Some other devices, you could be talking to them with granularity of blocks, and the size of the block could be different for different types of devices, but it's basically more than a single byte. For example, your disk or your network, you don't talk to these guys byte by byte. You talk to them block by block. The other thing is your device capable of being addressed randomly, or does it only accept sequential accesses? So for example, if you're reading a disk, you can actually jump to the end of it. So that's physically possible, to just go from one data point in your disk to another data point in your disk. Let's say you have a Blu-ray, or you have a DVD, or you have a CD. You can access anywhere in this. So it allows random access. But some other types of mediums might not be able to do that, right? For example, this if you have a tape, then you can't just jump to the middle of the tape. You have to just go forward in the tape until you reach your destination. Or if you want to go backward, you can't just jump. You have to just reverse and go back to where it was. So everything has to be sequential. So that's very important, actually. In fact, we'll see how this impacts file systems. I mean, I hope we get to talk about it, but it's important when you're designing your interface to know if sequential accesses are only permitted, or if random accesses are also permitted. Also, you might want to know maybe sequential accesses are faster than random accesses. Like if you have two accesses that are sequential, then the average time for each one of them might be much less than if the first access is here and then the second access is a jump to somewhere else. So these become important. Now, the other thing is the device capable of notifying the CPU? Or if it is, how? If you tell your device to do a certain thing, how do you check if that certain thing has been done? Or if your device is an input device, how do you know that an input has been provided? Now, some devices allow you to so some devices provide interrupts. They can raise interrupt when whatever they were supposed to do is done. They can raise an interrupt and then you can go and check. Some other devices, you have to monitor them to see when and if they finish the job they have done. For example, a serial port, you have to just ping it to know when the data has been sent or when the data was received. So going back to data access, this is an example where different data access require different interfaces. So if your device is a character device, if the unit of data transfer is a single byte, then usually in Unix-like systems, the interface, the system calls that you're going to use is usually get and put or get and set, where if you want to send a character to your device, you use system called put, and if you want to get a character, you use system called get. If your device is a block device like SSD, for example, or your CD or your DVD, then you usually use open, read, write, seek. This one for random access, obviously. What did I do? Random access. So this is something that you have seen in ECE 252. And then there are some devices that are kind of like different from both of these two. They kind of support both. For example, your network devices, they get their own categories. You open a socket, you listen to a socket, you close a socket, and the interface is basically the socket interface. When it comes to timing with regard to devices, you might have different timing interfaces. You might have some system calls to interact with the I/O devices that are blocking. For example, if you read or write to a file or from a file, then it might be blocking. So you say, I want to read this file, and you get blocked while the read is happening. Once the read is done, you get a notification that your data is ready. There are devices that you might want to implement a non-blocking interface. For example, just as an example, the lab that you're implementing, you have this send and receive system calls to be blocking. So if you send a message and the queue, the mailbox is full, you get blocked. Although I don't think that's a requirement for your case. Let's talk about receive. Let's say you want to receive and the mailbox is empty, you get blocked, and you have to wait until a message comes back. Now you could implement non-blocking receive. For example, your receive checks the mailbox. If there is nothing, it returns false, and then you continue. So this becomes a non-blocking interface. The same with devices. We could have non-blocking interfaces. For example, with your serial port, you could just look at the serial port. If it is ready, you can just read or write. If not, you just move on. And then you could have these asynchronous interfaces. I'm pretty sure, if I'm not mistaken, you covered this topic was covered in 252. So these are actually very handy in today's cloud computing and data centers, where the idea basically is that you say, I want to read this file, but I don't want to wait for it. I don't want to get blocked. I have other things to do. So you go and do whatever else you want to do. And once that's done, you get notification that the file that you wanted to read is ready, and you can continue. OK. Now let's talk a little bit about notification mechanisms that we talked about. So with polling, you're wasting CPU cycle. So this should be pretty obvious at this point for you guys, that if you're polling, you're wasting CPU cycle to just check the same thing again and again, to just wait for the device to be ready. This is bad in terms of CPU utilization, because you could have used your CPU time for something else. You just busy waited. But it's good for cases where data comes very frequently. So if you're receiving a lot of data, then it might not make sense to use interrupts, because then interrupts have overhead, because you have to have interrupt handler, you have to have mode switch and all of that, and you might not want to do that. So you might just want to, if you're getting a lot of data very frequently, then you're not wasting CPU if you just wait and you poll. The other one is obviously interrupt driven communication with the device. So in this one, the plus side is that you're not wasting CPU cycles on waiting. But the downside is that if you, this downside here, we have seen it in real-time systems where, it provides unpredictability, right? You're running your application and then an interrupt happens and the application gets interrupted. Now you don't know how long it takes for the interrupt to be handled. You also don't know how many interrupts you're going to get during the execution of your application. So it just totally makes your execution unpredictable. The other downside of this is if you frequently get interrupted, then the overhead of interrupt handling could become non-negligible. So that's another difficulty. And then you could have a hybrid model of using both, so which is usually used for high bandwidth networking systems, where for example, for your initial packet, you wait for an interrupt. When the initial packet, the header packet comes, then you're expecting more packets to come, then you can start pooling. So you could use a combination of the two. OK. Now let's talk a little bit about the architecture of I/O subsystem in hardware. So this is usually what you see in a typical modern system. It's called a north-south bridge layout. So the way it works is, you have your CPU here on top, and then you have, so the main components are the CPU and the memory, really, right? Now, the memory has a memory bus and a memory controller. So this guy is a memory controller. So everybody, including the CPU, sends their memory requests to this memory controller. Now, you have also an I/O controller, which you connect all your I/O devices to. And then there's a bus between I/O controller and memory controller. So, you know, your I/O devices also communicate with the CPU through memory. So they also, for example, if you have an SSD, you want to read a file, well, you're going to write data to memory. So your I/O system is going to talk to memory, and then once the data is ready, the CPU is going to go and read the memory. Now, initially in very early systems, the north bridge, so this memory controller and the I/O controller, they were both of them, they were off chip. So if you look at your motherboard, you would get a north bridge and a south bridge, and then, you know, all the I/O devices were connected to the north bridge. These two were connected, and then this would be connected to your memory. And then you would install your CPU. So and the CPU is connected to the north bridge. So this is your north bridge, and this is your south bridge. Now this system, this very, you know, I think this was Intel design back in days. Now AMD brought the north bridge into the CPU. So the CPU had north bridge here. So basically here you would just install your memory because the north bridge was on the chip. And then you would also connect your south bridge to your system. So now this brought a lot of performance benefits because then the CPU cores are talking to this memory controller at the same frequency that the CPU is operating. So there's, in this one, this north bridge could be operating in a very slower frequency than the CPU. So there is a lot of a slowdown when you're connecting them off chip. By bringing the north bridge to CPU, this gave a lot of performance benefits to AMD systems. Very recently, I think it was like, I don't exactly know when, but very recently, like in the past, at least at most 5 years, AMD processors, it might be actually the past 3-4 years, I don't exactly remember. AMD decided to bring both of these two on the chip. So both the north bridge and the south bridge in recent AMD processors are actually on the chip. So this, as you could imagine, gives you a lot of, so here you just install your memory, and here off chip you install all your I/O devices. And then both of them are on the same chip with the CPU. So this actually provides even further performance improvement as communicating with the I/O controller becomes really fast. And this made sense because the gap between I/O and memory was disappearing, right? I mean, it's the gap is not exactly disappearing, but it's getting closer and closer as you know, our I/O systems are becoming faster and faster. So that's a quick overview of I/O architecture in our processors. Okay, one of the main I/O protocols that is used in today's system is PCIe. Sorry, or the parent, which was PCI, and now PCIe. Now, this PCI, it just started its life as just parallel bus. A parallel bus was what it was initially. But it had, so if you go with the parallel bus, it has a lot of limitations. You know, multiplexing address and data on a parallel bus is really really hard, right? And then if you have multiple devices connected to this parallel bus, you have to make the frequency of this bus to be synced with the slowest device, because all of them have to be able to understand the messages on the bus. So if one of them is a slow, then the bus should bring itself down to the level of the slowest one. So they basically fixed this by introducing PCIe Express, another version of PCIe, another like a extension on PCI. They added this Express, and the idea was to go from parallel bus architecture to serial bus architecture, but what happened was they kept the interface the same. So the protocol remained the same as PCI protocol, but then the communication changed to kind of like a serial bus with packet switching and point-to-point communication. Now, each device, it's in the next slide. So each device becomes a PCIe endpoint, and you get these switches that connect one or two or bunch of PCIe devices to the main interconnect. And the way that the devices talk to each other and to the memory is through sending packets. So this is very similar to how internet works, how Ethernet works. It's kind of like just message passing, packet switching on a network on chip, connected network on chip. Now you have different lanes, and devices can use different number of lanes. The more lanes a device uses, the higher speed it can get. So each lane provides a certain bandwidth. The more lanes you use, the higher speed you can achieve. Now, if you have a slow device, you don't need to bring the speed down to that device. Because each one of them has its own connection, you don't need to bring down the entire system for a slow device. And as I said, the magic, why PCIe actually really shined and became this popular was because they didn't change the abstraction layer. So they kept the protocol the same. They added features, but they allowed old devices that were working with the PCI protocol to still work on PCIe connection. And that really added to the popularity of PCIe. And if you ask me today, PCIe is just becoming the common interface for I/O devices. So most of our I/O devices, our network cards, our GPUs, most of them are now on PCIe. Even some USB devices are now using PCIe connection to connect to the rest of the system. And that was mainly because they kept this interface alive, and they kept this backward compatibility possible. Now, as engineers, this is one of the things that we have to take lessons from. When you're designing, it's always like good to think about future and design something that is future-proof. That you don't need, that it has the potential to be extended, but at the same time, it also meets all the needs that you have in present. So here is an example. Going back, this is the memory. This is your CPU. The connection is called root complex. Each device can connect to this, or you could put a switch and connect multiple devices. Now, the PCIe allows other protocols to also talk to it. So you could have a PCIe to some other protocol, in this example, PCI, PCIX, or SATA, or any other protocol. You can put bridges and then connect devices to this bridge that would then be able to talk to this root complex. Now, this architecture allows endpoints to talk to each other. It allows CPU to talk to devices. So when you run your device driver communicates with the device, and then your devices could talk to each other because they can send packets to each other. Your PCIe devices could also talk to memory. They can, let's say it's your SSD, it can do a DMA to memory, write data directly to memory, and once it's done, it can raise exception. Now, apart from this architecture, let's talk about I/O devices and I/O controllers. So let's assume that you're connecting this. Looks like what is this device? It looks like it might be a GPU. I don't exactly know what kind of device it is. Yeah, if you guys know, let me know. It could be a network. No, that doesn't look like a network. Anyhow, so whatever device that is, let's say you connect it to PCIe, and by the way, this is the connection. This is the usual PCIe connection. So you connect it to your PCIe system. Usually, internally, your device has a controller. So this is implemented inside your device. This is a device controller. You usually have a PCIe engine or PCIe interface that is in charge of communicating with the rest of the system. Now, the device usually has some registers. These registers are mapped to physical addresses. So when I said that the device driver talks to the device, usually it's through writing to these registers. So it sends commands to these registers. And you also have some buffers. So for example, you could have data buffer, or you could have some control buffer that you can read or write data to. These are also mapped to usually mapped to memory addresses, physical memory addresses. Okay. Now, yes. So CPU communicates with the device through reading and writing to these registers and to these buffers. During the boot time, when your system boots, usually PCIe devices configure the mapping. So this mapping that I said, that these are mapped to physical addresses. This mapping usually happens during the boot time. It's called the configuration space register. So there are registers here called configuration space registers. In every PCIe device, you have these registers. In fact, in every PCI device, you have these registers. So when you turn on the device, it sets those registers, and these registers basically tell the system how many registers there are, what is the size of the buffer, how many buffers there are. So the device sets these registers. Now at boot time, your system will recognize all these registers and starts allocating physical addresses to these registers. And once the mapping happens, and this is usually actually before the operating system even comes up, sometimes operating system does it, but usually it's the BIOS that does this. So it once it maps the device to a range of physical memory, so once it says, okay, I have mapped your registers to this range of physical addresses, it writes to the same register that initially the device set to tell the system how much memory it needs. Once the memory allocation happens, address mapping happens, the BIOS writes to those registers to tell the device that you are mapped to this range. Because the device also needs to know where its registers are mapped. Because later on, when the device driver starts communicating, you want to know that it's communicating with you, because you are listening to all the messages that are sent on the network. You want to detect that this message was sent to me because it's using my addresses. So basically, if the same register is used for telling the system what you need, and then system telling you where you're mapped. I guess I'm going to stop here for today's lecture. So we'll continue from here on Tuesday. Thank you so much for sticking around, and we'll talk to you on Tuesday. Bye.